All right, let's get on to unit number 7, where we're talking about torque and rotational motion. So as we launch into this, I want to make sure that we remember what center of mass is. Center of mass, simply put, is kind of like the average location of all the mass weight. It's not always going to be on the object. It's not so much of a physical location, more of just like helping us to understand that central point. It sometimes can be thought of as a balancing point because if the center of mass does exist on the object, that point is the point about which everything will be balanced. And so closely related to that is something called center of gravity. Now, center of mass and center of gravity are very often the same thing. However, let me clarify that. They are very often at the same location. However, they are not necessarily the same thing. All right. So the center of gravity is simply it's simply where the force of gravity appears to be acting on the object. And typically this occurs at the same location as the center of mass, and so we often treat them the same way. You probably won't really need to know much about that, but in case you see the phrase center of gravity, I wanted to make sure you understood that. So far, when we've looked at forces, even if you didn't realize that this is what we were doing, we've always been working with the center of mass of an object. So my question is, take a look at this picture. What would happen if somebody exerts a force? We'll call this point right here the center of mass. What if someone exerts a force on an object and it doesn't go directly through or towards the center of mass? What would this object start to do? Well, it's actually going to start to rotate. And it's going to rotate around this center of mass. And in this case, the force is going to push it in a clockwise direction, which, if you recall, we said is the positive direction. So how about this? What direction would the block move if the force was applied as shown? Well, here it's going to move in a clockwise or negative direction. We call this clockwise, counterclockwise. We refer to this as rotational motion. This isn't just circular motion. This is the actual object itself rotating. When we've talked about circular motion before, the object itself wasn't really rotating. It was more of that the object was moving in a circle around something else, a different location. In this case, the object itself is rotating around its own center of mass. How about this situation? We've got two equal forces on opposite ends. What direction would the block move? In this case, it's actually just going to move in a straight line to the right. It's not going to rotate at all. This is what we mean when we say translational or linear motion. It's not rotating, it's just moving in a straight line. So one of the things to consider is that a lot of the basics and the equations that we started the year out were linear or translational motion, and they have a comparable rotational motion. So instead of displacement, which is simply how our position changes, we're going to talk about angular displacement, which is how the angle changes. As an object is rotating, how much is that angle changing? Velocity was displacement over time. Angular velocity is angular displacement over time, or the rate at which the angular displacement, or the rate at which the angle is changing. Acceleration is change in velocity over time, and it's comparable to angular acceleration, which is our change in angular velocity over time. Likewise, we can take our kinematic equations, right here, the three main ones we used, and we can translate them into rotational motion. So instead of velocity, we have rotational or angular velocity. Instead of acceleration, we have angular acceleration. The time, that one stays the same. Position, and angle. So it kind of just varies. But I seriously doubt you're going to have to use these equations. If you get hit with them at all, it's most likely going to be more of a conceptual understanding. But in all honesty, ladies and gentlemen, if you understand how to use the regular kinematic equations of motion, you in turn will understand how to use these equations because they're the same, just we're just calling the variables something different. So I would give a focus to understanding these equations. All right. So whenever an object rotates, it's going to have a point about which it's going to rotate. Sometimes when we have a fixed point, we call that our pivot point. Sometimes it's also called the fulcrum. All right. So take a look at these two images. Identify the fulcrum or fixed pivot point for each of these objects. Well, for the seesaw, it's going to happen to be right here. This is going to rotate down. This will rotate up. This is the only part that stays stationary. If we look at our door, there are 3 hinges here that allow it to rotate. So this whole area right here is going to be the fulcrum. It's the point about which that door will rotate. Now, when we analyze forces that are acting on an object, it's not enough to just look at what the forces are. You also need to look at where they're located. How close or far away are they from the fulcrum? The distance from the fulcrum to where the force is, we call that the moment arm or the lever arm distance. Okay, so you can actually try this even though you're not at school. You can try it at home. Just find a door. All right, find a door, and what I want you to do is first push the door open with one hand. We'll say pretty much right above the doorknob. You could go right above the doorknob. Then try to push the door open again with the same hand in the same way, except put your hand in the middle of the door. So right in the middle between the hinge and the doorknob. And then the third time, you could try to push the door open with the same hand in the same way, but put it just on the door, very, very close to where the hinge is. Okay. Here are some guidelines to help you be consistent in how you push the door. You may have to adapt. I'm not going to read them. You may have to adapt this depending on the door that you're using. When I wrote this, I had the doors into my classroom in mind. So when you do this, go ahead and pause the video and do this. But keep in mind, I want you to make some observations about what that's like. So after you try this, what did you notice? And try to think about how the lever arm distance affects the rotational motion of an object. Well, what you should have noticed is that the closer you are to the hinge of the door, the harder it is to push the door open. There's a reason the doorknob is put on the opposite side of the hinge. The reason for this is the answer to the second question. When you have a large lever arm distance, rotational motion is easier. The smaller the lever arm distance, the closer you are to that pivot point or fulcrum, it's so much harder to get rotational motion to occur. So we place the doorknobs on doors in a place where they have a large lever arm distance. That makes it easier to open the doors. All right. Now that we've talked about that distance, let's talk about forces. So most of the time, when we're looking at a force that's causing rotational motion, we are only interested in the forces that are perpendicular to the actual lever arm distance, okay? So if this arrow was going straight out and it was parallel to the lever arm distance, that's not going to cause any rotational motion whatsoever. We're interested in perpendicular. So if you get a force at an angle like this, you're going to have to break it into component parts so that you can use the perpendicular portion. For what we have set up here, we got the force multiplied by the sine of the angle is a pretty common way that we express the perpendicular portion of the force. So there is a more specific definition, a more technical way to figure it out. If you happen to have a 5 steps to a 5 for AP Physics 1, page 135 is the place to look to learn this. I don't care about it because the method that I use, in my opinion, is simpler. It's faster. So I'm not going to bother trying to explain this right now. But if you happen to have that book, you're welcome to check it out. So this force, let's look at this in practice. If the force shown below is 100 newtons and the angle is 60 degrees, how much of this force causes the object to rotate? Or in other words, what is the perpendicular component of the force? Well, you should get 86.6 newtons. You're going to go back to our force multiplied by the sine of theta. So you're going to do your 100 newtons multiplied by the sine of 60 degrees. You should get 86.6 newtons. All right, so now one of the things we talked about is that a force can cause an object to rotate. It can cause it to twist. This twisting motion, we call that torque. All right, now torque is a vector, and it's very comparable to how forces behave on objects. All right, so to determine the torque that's acting on an object, you have to look at both the perpendicular part of the force, and you also have to look at that lever arm distance. Okay, the force and where it's located compared to the fulcrum is what's going to determine the torque. Okay, your equation sheet says to use the perpendicular portion of the lever arm distance. You can basically just use the perpendicular part of the force. You should be able to get the same answer. Maybe a little bit easier. Okay, this little symbol right here is the Greek letter tau. Greek letter tau. Make sure it doesn't look like a T, otherwise AP graders might think that you are saying that time equals this, and that's not correct. It's torque equals that. So instead of including the force or the moment perpendicular force or the moment arm distance that's perpendicular, we can just substitute all of that in, and you get torque equals to the lever arm distance multiplied by the force multiplied by the sine of the angle between the lever arm distance and the force. So let's practice a little bit. I want you to take a look at this situation. This right here, this black area, is our pivot point. We have a variety of forces. You don't need to worry about all these forces being pushed at the same time. Look at each one individually, all right? Each little section is half a meter. So this is half a meter, 1 meter, 1.5 meters, 2 meters. I want you to look at this, and I want you to tell me, out of all these forces, which one provides the largest torque? Or if they're tied, which forces provide the largest torque on this object? Well, you actually are going to get 3 of the forces are tied for providing the largest torque. Force number 1, force number 2, and force number 5 all provide the same amount of torque with 100 Newton meters. So, like I said, torque is kind of like the rotation version of force. We're gonna look at right now the rotational version of inertia or mass. Okay, so remember, inertia describes, or mass just helps us understand an object's natural resistance to any change in its motion. Rotational inertia, comparable to mass or regular inertia, just lets us know how much the object is going to resist any change to its rotational motion. Sometimes it's called the moment of inertia. It's an older way to say it. You're probably more likely to see rotational inertia, but this is the equation. Your rotational inertia equals the mass multiplied by the distance from the axis of rotation, the distance from that pivot point, okay? You can use rotational inertia the same way that you would use mass for an object that is rotating, all right? So here's what I'd like you to do. Since torque and rotational inertia are the counterparts of force and mass, respectively, and since angular acceleration is the counterpart of acceleration, I want you to take Newton's second law, and I want you to write it using rotational motion variables. So in other words, what is Newton's second law for rotational motion? Oh, that slide's out of order. Whoops. So since torque is the rotational counterpart, here's what our we're going to replace the force with torque. Okay, so we have Newton's second law right here. So instead of force, we're going to replace that with torque. Instead of mass, its counterpart is rotational inertia. And instead of acceleration, we have angular acceleration. So this is Newton's second law. This is Newton's second law for rotational motion. Now let me go back to what should have been the next slide. So you got to keep in mind, just like we talked about when we were looking at dynamics, you can have multiple forces acting on an object at the same time. Well, it's also possible to have multiple torques acting the same way. So we're going to be looking at rotational dynamics. You're going to use Newton's second law for rotational motion to help you understand it. Now, sometimes when we are looking at this, you can have multiple of these forces that kind of cancel each other out, just like how we've had the net force equal zero. Well, it's also possible to have the torques canceling each other out, having the torques equaling zero. All right. So the key word is static equilibrium. Whenever it talks about how a system is in equilibrium and there's rotational that's possible, but it's in equilibrium, that's going to tell us that there's no angular acceleration. All of these torques are adding up to be zero. Okay, so let's practice with this. A 50-kilogram girl and a 60-kilogram boy are sitting on a seesaw in equilibrium. If the boy is sitting 0.75 meters away from the fulcrum, where is the girl sitting? So what is the girl's location? How far away is she from the fulcrum point? Well, we're going to launch right into Newton's second law for rotational motion. So this is Newton's second law for rotational motion. Notice, let me go back to the picture. The torque for the boy is going to be his weight, which is this times the force of times the acceleration of gravity, multiplied by his lever arm distance. Same thing for the girl. It's going to be her weight, this times the acceleration of gravity, multiplied by her lever arm distance. That's where we get this from. The weight or force of gravity of the boy multiplied by his lever arm distance. I'm using X right now instead of R. And then the weight or force of gravity of the girl and her lever arm distance, that's going to equal our rotational inertia multiplied by the angular acceleration. So all I do next is I substitute the weight equation. So mass times the force of the acceleration of gravity. I substitute those in. Okay. Notice one thing, something else I'll point out. The boy has a positive torque and the girl has a negative torque. If we look at the picture, in this situation, the boy is trying to push this in a counterclockwise motion, so he has a positive torque. The girl will be trying to push this, the weight of the girl is going to try and push this in a clockwise motion, which is negative. That's where that negative comes from. Now, in this case, it's in equilibrium, so all of this is going to equal zero. So we can set these two torques equal to each other. So when we do that, you can solve. When we do that, you can solve for this lever arm distance. Once you input your values, you should get 0.9 meters. 0.9 meters. All right. So if you have the 5 steps to a 5, here's a good section to read. Otherwise, that's basically it. There's really not a ton to this. A lot of this builds on stuff that we've already talked about. Kinematics, dynamics. A lot of it's going to be very similar in that respect. It's just we're going to be looking at an object that's rotating instead of linear motion. So this was a challenge I had you guys do in class. You could actually try doing something like this on your own. You just have to be able to find something that balances and is able to rotate. Get some things where you know the mass or the weight of the object and see if you can calculate where to position them so that the object stays in equilibrium. It could be a nice little challenge. You'll have to work the equations, and it'll be a practical way to try and test out some of the stuff that we've learned about. So anyhow, that about wraps it up. This one's a short one, but hopefully it's been informative. And as always, let me know if you've got any questions.